Yeah, so welcome to this talk on quantum computing as part of the Support Vectors meetups. This is an introduction talk in this space, and we may have follow-up lectures on more complex topics in this area. So just to introduce you to the area itself from a physical angle, um, you all probably are familiar with the double slit experiment in physics. And you have there's a screen with two slits, and you throw a whole bunch of photons on it, and you end up getting this interference pattern on the screen. And uh, this is the wave particle duality conundrum that's there. And um, is light traveling as waves or as particles or both, or is it a wavicle and things like that? So the interesting thing is now, so we may think, oh, okay, maybe two different photons interfering with each other and creating this interference patterns as they come out of the slit. But the interesting thing about this thing is if you slow the system down so that you're just sending one photon at a time, it still produces this interference pattern. That photon, or even a particle as you send it, a really tiny particle as you send it to the screen, it interferes with itself and then goes and produces, it hits the screen at different places, different particles hit at different places, and then produces pattern, which is the weird thing about it. Um, so if we thought that two different photons were going through two different slits and interfering with each other, when we slow it down, a portion of the photon goes through uh, each slit and then kind of combines and produces this. And somehow they have the knowledge that they have to produce this interference pattern. So a sequence of photons as they go through, they actually know that they are a family of they represent a behavior that should be shown on the screen, which is like this. So this is where it comes from. And for these um, um, and when the particle hits the screen, then you make a measurement. At that point, it collapses to a particular state. So in these equations, we have um, uh, these are some of the physics equations. You have E equals h times the frequency, or h bar omega, where omega is 2 pi f. You have other equations like de Broglie's equation that tells you what the wavelength is as a function of Planck's constant and the momentum. And then you have energy equations, for example, where energy is p squared by 2m. Now, the system is actually defined by a group velocity, and then the velocity of a particle is a group velocity of a packet that is constructed by a superposition of waves, and this comes from this results in a wave function for the particle. So when we say superposition, you can actually think of it as an integral over this function here. The phi k here is can be different amplitudes of the wave, and then the superpositions of the wave integrated over the different possible values of k ends up becoming a wave function. And it's possible that this function peaks out. It doesn't actually, it is not a point function, but actually has some sort of a wavy behavior around some, say, peak value of K. And around that, you can do an expansion of this thing, of the W of K function, and then start studying the behavior. So effectively, there's this whole, and that results in the psi, which is called the wave function. And these and the wave function is uh, satisfies this equation of motion where you have IH bar d psi by dt is H psi, where H is the Hamiltonian or the total energy of the system. Now we will see that um, uh, when we have a wave function, um, when we think of quantum particles, uh, the wave function of the particle can be described as a superposition of different states. And let's say we have two states, say 0 and 1. And this can be spin up and down, for example, um, uh, uh, or a light polarized, left or right polarized, and so on. So the wave function is written as a sum of as a weighted sum of the different states, different possible states in the system. Now these alpha 1, alpha 2, they're essentially the amplitudes, and the square of these amplitudes, when you add them up, that is effectively the sum of the probabilities for the different possible states. And the sum of the probabilities should add up to 1. Now these amplitudes, they can be complex in general, and so then you would take take alpha 1 and its complex conjugate to kind of get the modulus here, modulus squared. Now we can see that effectively as we put this thing through a screen, for example, through, say, going through a polarizer and stuff, and let's say the photons are arriving at some angle alpha, then it depends on on that angle and how much energy gets transmitted going past the polarizer. And so if you think of the photon arriving with a magnitude A at an angle alpha, then think of A cos alpha as the amplitude that is going through the polarizer. Then effectively, we know energy is the square of the amplitude. So that is proportional to cos square of alpha. And the total energy before it went through the polarizer would have been A times cos square alpha plus sine square alpha. Cos square alpha plus sine square alpha is 1. So total energy would have been A square cos square alpha plus A square sine square alpha. But the A square cos square alpha is going through and through the system. So effectively, the probability of the photons, the fraction of energy that's going through the polarizer is given by cos square alpha. So this is where you can see, like, you can say the photon you can think of two versions of the photon, one that's going through the polarizer and one that doesn't. And the amplitude for the one that goes through is cos alpha, and the one that doesn't is sine alpha. So now you can effectively see why the squares of the amplitudes are considered as probabilities in quantum computing, because it comes from conservation of energy to some extent. So you can say the amplitude is cos alpha, so the energy is proportional to cos square alpha, and the sum of the energy is conserved. So the sum of the probabilities is conserved. So a lot of the time we wonder when we see this kind of a wave function depiction in quantum computing, we see these amplitudes, but then we say the squares of the amplitudes add up to one. And so to a large extent, these corresponds to um, actual wave amplitudes, for example, and the probabilities correspond to energy in the system. So that's one way to interpret that. Now, these photons can be in a superposition of states, and if you observe it, then it collapses to one of the states in the system, and then you know if if it was in, let's say, if it had a probability of alpha 1 square of being in this state, say spin up, and a probability alpha 2 square of being, say, in a probability 1, uh, then um, the uh, when we actually do the computation and do the measurement, it could collapse to either this state or this state, but once you measure it becomes that state. So, but until you observe, it could be in any one of the two states. And this is the famous Schrodinger's cat problem, where the cat is hidden, and we don't know if it got exposed to a poison vial and whether it's alive or not until you actually observe it. So the measurement causes a collapse of the state. The moment you open the lid to see the cat, then you will know whether it is alive or dead. But until then, you don't know. So that's the measurement problem. And also, because it's all probabilistic, you can't, and you don't know what the probabilities are actually until you can't, because you don't know the actual amplitudes, you can't clone these particles. But there is a way. When we do quantum computing, there's also an area called quantum inspired computation, where we can actually uh, simulate quantum processes. And so we can define a variable. And if you define a variable and try to do some quantum processing in a classical computer, you could, for that variable, as you do the computations, you can actually see what the amplitudes are for the different states. So, but you're technically not supposed to see it, but you actually have that information available. So there is a possibility of doing some richer computation in the classical side by actually using the knowledge of the amplitudes that you have, because you can actually observe um, these amplitudes because it's going through a program. Now, sometimes quantum libraries deliberately hide it so that you're not supposed to see it. But if you can expose it, then you can actually see it. And so maybe with that knowledge, you can actually do some more interesting computation, because in a true quantum computer, you can only measure and then try to do computations. So there is a possibility. There's this interesting area where you're trying to do quantum-like simulations on a classical computer, which could have which could also produce interesting results. So in general, you have different states. Like I said, polarization of light, or electrons with different spins and things like that. And this, I mean, the straight line with the right arrow that you see, that's called a ket. So this is ket 0, and it's represented by this basis vector 1, 0. Similarly, this is called ket 1 and can be represented by a basis vector 0, 1. And so the overall wave function that is represented by a superposition of these two states. It can be written as a weighted sum of these column vectors individually as basis vectors, or you could just write it as the amplitudes in a column vector, for example. And if the two states are equally probable, with real amplitudes, for example, then typically you have 1 over square root of 2 in front of them. And when you square this, then you get half plus half and you get a 1. So the squares of the amplitudes, as we said before, add up to 1. And these can in general be negative, complex, for example, right? So, but we're just showing here with real values. You can have another particle B, which can be represented as a superposition with different set of amplitudes, for example. Then the combined state of the two particles is given by what's called a tensor product. And we'll see what it is, how we evaluate it. But essentially, you take the state of one and do a tensor product with the state of the other. And when you do that expansion, essentially, of this, essentially are doing tensor products across these basis vectors and having 4 possible values here for amplitudes: alpha 1, beta 1, alpha 1, beta 2, alpha 2, beta 1, and alpha 2, beta 2. And this can, in a simplified notation, ket 0, tensor product ket 0 is written as just ket 0, 0. And similarly for the others. And how do you actually evaluate the tensor products? We'll come to it in a bit. So in general, if you have 2 qubits, for example, you would have this state representation as a combined state representation of the 2 qubits. And then if you do the calculation for this across and sum all the probabilities by squaring these amplitudes, you'll find that they all add up to 1. So now, shouldn't be too scared of tensor products. It's just column vectors, and here's how you do it. You just take, say, ket 0 is 1, 0, and ket 1 is 0, 1. So, for example, look at one tensor product 0 here on the right side. So what you do is you push, you take ket 1, when you're trying to do ket 1, tensor product ket 0, take ket 1, and adjacent to each of the elements of the column vector 1 of ket 1, push ket 0 into it. So here, for example, 1, 0 is right next to 0, and another 1, 0 is right next to the 1 here. And then you multiply these two, and now you get a column vector which is 4, which has a dimension of 4 here. And so you get 0, 0, 1, 0. Similarly, if you do 0 tensor product 1, then you start with 0 and then push the 1 into it. So push the column representation for 1 into it, and then you get 0, 1, 0, 0. 0 tensor product with 0, you just get 1, 0, and you push the 1, 0 into it, you get 1, 0, 0, 0. And then if you do the ket 1 with ket 1, we should get 0, 0, 0, 1, right? Because you have 0, 1, and you push the 0, 1 inside, and the only last 2 ones produce the 1 here. So effectively, you create a longer column vector. And so these are the basis vectors, right? So so it's 1, 0, 0, 0, or 0, 0, 1, 0, 0, or 0, 0, 1, 0, and 0, 0, 0, 1. So now it's clear, right? We have, when we look at this combined state, all we have is, instead of like a column vector which was too long, 2-dimensional long, which had a dimension of 2, now it's a dimension of 4 with an amplitude alpha 1, beta 1 sitting in front of it. So 0, 0 we saw was 1, 0, 0, 0, and then 0, 1, 0, 0 for the second one, 0, 0, 1, 0, and 0, 0, 0, 1. So, and you have 4 different amplitudes. Yeah, so we just went through this. And also there's this concept called an inner product. So what we were seeing until now was the ket, and there's a complementary representation called the bra. And you can do an inner product of the bra with the ket, and effectively that's like taking a row vector with a column vector and doing a dot product. Um, um, and you can have additional multiple states as well. If you have k qubits, so we saw with 2 qubits, we had 4 states. And if you had 3 qubits, you would have 8 states. You would have A1, B1, C1, A1, B1, C2, that kind of thing. So you'd go and expand it out. And you would have these, each of the basis vectors would now be, if you had 3 qubits, then each of the basis vectors would be 8 long, for example. It'll start with 1 and followed by 7 zeros, and 0, 1, and then 6 zeros after that, and so on. And again, all the probabilities will still add up to 1. Just like we did for the two photons, we can do it for any number of photons, and we can still show that it adds up to 1. And you must have heard a lot of talk about gate-based quantum computers. And essentially what they do is they take these column vectors and transform them. And so the transformations on them are done using unitary matrices, so which have a property that if you take the conjugate transpose and multiply it with the matrix, then you still get the identity matrix. So you can, the H here is called a Hadamard gate. For example, this is an example of a unitary matrix. And if you take, if you do the computations, you can see that it does end up being the identity matrix here. So in general, all these gates have this are unitary in nature, and there are different types of gates, and based on, and effectively they're trying to do some sort of rotation on these vectors. If you start with 0 and with get 0, and then you apply the Hadamard gate, you can see now you've kind of moved it into a 45-degree direction. And similarly, if you apply it to ket 1, it's moved in an opposite direction here. So, it essentially, you can see that if you use the Hadamard gate and you start with 1, 0, you end up having components in both dimensions. Or if you start with 0, 1 as a basis vector, you apply the Hadamard gate, now you have components in both dimensions. And so this is kind of typically used at the start of quantum computation to create, to transform a qubit into a superposition of states. So it's a trick that typically is used at the start of quantum computation. Now you can see here, if you have ket 0 if you think of the basis vectors and ket 0 is say pointing along the x-axis and ket 1 on the y-axis, you can see when you have 1 over square root of 2 and 1, 1, you're effectively doing a 45-degree rotation anti-clockwise. And if you take 0, 1 and you rotate it and you apply the Hadamard gate, so 0, 1 is ket 1, which is pointing along the y-axis. And if you apply the Hadamard gate, now it's pointing in the fourth quadrant down here. So at a minus 45 degrees. So it has actually turned by 135 degrees clockwise. So, so the geometric interpretation, there are different ways to interpret this. One can be that it's a reflection. For example, this transformation of 1, 0 to the direction 1, 1 can be viewed as a reflection around the pi by 8 direction here, right? Um, uh, 45 degrees is pi by 4, so it's rotation around pi by 8. And but if you take 0, 1 and you still draw this line pi by 8, now essentially get 1 is getting reflected. If you reflect that, and it goes down to the 135 degrees. So essentially this unitary transform can be viewed as a reflection around the direction pi by 8, regardless of what you start with. If you start with 0, you go here. If you start with 1, you go here. So that's one interpretation. The other is another way to say it is, hey, rotate clockwise by pi by 4 and then reflect around 0. So you can see, if you can say, hey, I can do a rotation and then a reflection around 0, then that will take you here. So for ket 1, starting on the y-axis, if you rotate clockwise by pi by 4, you end up, you're now at plus 45 degrees, and you reflect around 0, you go to the minus 45 degrees. So this is actually effectively a product of two matrices, one which says, hey, let me rotate by pi by 4 and then reflect around 0. So all these unitary transformations can be sort of considered as rotation or reflection or a combination of rotation and reflection geometrically. And I don't know if you guys attended one of Asif's lectures on how we interpret matrices, and when we're talking about eigenvalues and stuff like that. And you can view all of that with these kinds of simplistic transformations. So this is showing up here as well. So this is typically, these are the other kinds of matrices. These are called Pauli matrices. Sigma 1, sigma 2, sigma 3, or sigma x, sigma y, sigma z, and so on. And there's another gate called C0 gate, which says it acts on 2 qubits, and it's used for entangling these qubits. So you've heard of quantum entanglement. This gate actually helps in that. So the way it works is there is a control qubit. If that control qubit is a 1, then it flips a target qubit. So for example, if you have this state 0, 0, 0, 1, 1, 0, 1, 1, it transforms this thing. When the control, for example, here, the first qubit we'll say is a control qubit, then the second qubit gets transformed. It gets flipped. So 0, where we have gamma 3 and ket 1, 0, that becomes 1, 1, because 1 is controlling. The control bit is a 1, and it says 0, hey, flip to a 1. And for gamma 4, the control bit, the first qubit is 1, so it says next qubit, hey, flip yourself to 0. So 1 goes to a 0. But if you see gamma 1 and gamma 2, the control, the first qubit is a 0, so nothing happens to the second qubit. It passes through. So essentially, the C0 gate says flip the second qubit if the first qubit is a 1. The first qubit is a control qubit. The second qubit is a target qubit. And now, we've heard of quantum entanglement. Internally, there are some physical processes that are used to actually achieve entanglement. But from a computation perspective, it is realized using these kinds of unitary transforms. Now, when two particles are entangled, then they can be directly entangled or inversely entangled. That is, if one particle is at ket 0, the other one will also be ket 0. Or if one is at ket 1, the other one will also be ket 1. So if you observe one to be ket 0, the other one will be at ket 0 as well. If they're directly entangled. If they inversely entangle, then if you observe one to be ket 0, then the other one will be a ket 1. So if one is spin up, then the other is spin down, if they're inversely entangled. Now, here you can notice that if they're directly entangled, you don't have the state 0, 1, and 1, 0. You only have the possibility that you have 0, 0, and 1, 1. Similarly, if they're inversely entangled, you only have state 0, 1, and 1, 0. You don't have the state 0, 0, and 1, 1. Now, this is basically saying that you cannot, when you have this kind of system, you cannot factorize it into two independent wave functions that we saw in the beginning. Where did we see this? For example, here. When we expanded it out, we had all four possibilities, but when you're entangled, you only have, if you're directly entangled, you have only this 0, 0 and the 1, 1 component, or if inversely entangled, you have the 0, 1 and 1, 0 component, and you cannot factorize it back to independent wave functions for each of the particles, like saying, hey, psi b is beta 1 plus beta 2, and psi a is alpha 1 ket 0 and alpha 2 ket 1. So the fact that you cannot factorize it makes the system entangled. So they are dependent on each other. Now, how do you actually create these entangled bits? You apply the Hadamard first to one qubit, and then you apply the C0. So when you apply the Hadamard, it transforms into this way. You have all these 1 over square root of 2s. Then if you apply the C0 gate, you end up having this kind of before you apply C0, you have this result, and then when you apply C0, this 1, 0 becomes a 1, 1, and then you get this entangled state. So you really need the C0 to kind of make this create this entangled state, because this target qubit is a 1, target qubit is a 0, and the control qubit is a 1. It flips it, makes it a 1. And so a lot of computation can be accomplished using these unitary transforms, and including entanglement. So now internally, there are a lot of physical processes that are being utilized, and these computers processing at near zero temperatures and things like that. Really super cool to know that. But it's all abstracted away in terms of just computations on quantum registers with matrix transformations being applied to them. Internally, we have to thank the physicists for helping us realize those computations internally. So now we come back to this qubit. We can say a single qubit quantum register can be represented as this, alpha 1 times the ket 0 and alpha 2 ket 1. And you can say a 2-qubit register can be represented like this, right? And a 3-qubit register can be represented like this, and so on. So when we say somebody has 53 qubits, they basically can go explore 2 raised to 53 possibilities, right? Um, so that's where the power of quantum computing comes in, because you have all these states simultaneously being explored with different amplitudes. And as you search the space, and maybe you're searching for something, maybe you're searching for alpha phi, then as you do your quantum search, the amplitude for this, for say alpha phi, will start increasing, and then you will come up with get this vector corresponding to alpha phi as the solution for your problem. So that's the interesting part about using these quantum computers to solve problems. You fool around with these amplitudes and tweak them, and finally you find an answer as one of the states in the system, um, based on which amplitude went up. Now, you really don't know what the amplitudes are, like I said, until you make a measurement. So when we do quantum computations, we are actually trying to transform these amplitudes with the hope that one of these amplitudes maybe has a high value, so correspondingly its probability of that state is high. So alpha phi, if its amplitude is higher, then the likelihood of the solution being the state corresponding to that amplitude is higher. So most of the time, we actually should do repeated computations on a quantum computer, because you're taking measurements, it's still probabilistic. And so you have to kind of repeat that, and hopefully you will see this solution emerge after a few iterations, because you observe it more often. Now, when we think of we can think of a physical quantum computer where we don't know the amplitudes. So if you try to create like a JSON data structure, it may look something like this. It has these states, but we have no clue what the amplitudes are, right? We just set up the quantum variable, we send it to a quantum computer and say, hey, set me up with this quantum variable with 2 states, right? Now, you could have a virtual quantum state variable, which is actually running on a classical computer, for example. In that case, you actually can potentially see the amplitudes. Now, sometimes libraries don't want to expose the amplitudes, but you could do some richer computation, as I mentioned, if you are aware of these amplitudes. So that's one thing. And if you have something that's entangled, then you can say, hey, is it directly entangled, uh, or is it inversely entangled, and so on. So, um, you know, and you could play around with these variables. Now, typical quantum computers are gate-based. IBM, Intel, Google. IBM has been increasing the number of qubits available. When initially it used to be 53, went to 127. It was called the Eagle quantum computer. And then the Osprey had 433, and now the Condor has 1121 qubits. Intel has a 12 qubit chip. So they're trying to put qubits on a chip. Google, I think, is still steady around 72 qubits. Then there are annealing-based quantum computers, which have these qubits arranged in an array. I'll show pictures shortly. And those are like a mesh of qubits, and their weights corresponding to those connections between the qubits. And those kinds of qubits are used for annealing-based computations. So D-Wave is a leader in this area for these kinds of computers. And both kinds of quantum computers exist this time. And so typical quantum processing is, hey, I will do some processing on a classical processor. Then I'll set up some variables for the quantum processor, let it do some computation, and I'll take a measurement and get the result back. Then based on that, maybe I'll make some changes, tweak it further on the classical side, and send it back again, and so on. So you could have an iterative process between a classical and a quantum processor. And it's possible that as you continually iterate through this, you might be increasing the amplitude of one of the states, which can become a higher probability state, so that when you make the measurement, that becomes a solution in the system. For example, one of the algorithms for factorization is Shor's algorithm. It's composed of two parts. The first part tries to turn the factorization problem into the problem of finding the period of a function. So it just transforms it, saying, hey, I'm converting it into a form where I have to find the period. And the second part actually finds the period using a quantum Fourier transform, and that executes on the quantum computer. That is responsible for the quantum speedup. So they work hand in hand. There's some classical computation that works alongside the quantum computation, and so the process can be hybrid or iterative in general. So for example, with Shor's algorithm, you're trying to find this period P, and a Fourier transform is performed that is trying to discover this period P. And if it is found, then the encryption key can be broken. So this is one of the algorithms. Then you have search kind of algorithms where you're trying to find something which has a higher amplitude. For that, there are the oracle and reflection transforms, where if you apply an oracle transform, you flip the state. So if the amplitude is, say, 1/square root of n, it flips to a negative 1/square root of n. And you can also apply reflection transforms, which is like which are of this form, which is 2 ket psi bra psi minus I kind of thing, and that magnifies the amplitude of a particular state. So you flip a state, and then you apply a reflection transform to amplify the magnitude of a particular state. And you can use this repeatedly to amplify states. For example, if you apply a reflection transform on, say, on position K, then effectively that's saying that I'm starting with the initial wave function, but I'm subtracting 2/square root of n sk for state for wave basis function sk, for example. So then the amplitude for sk goes from 1/square root of n, say, to minus 1/square root of n, because psi contains sk itself with the amplitude 1/square root of n. And then you're applying the reflection transform. When you apply the reflection transform, you can see that the new wave function has all the other states with a reduced amplitude, and the state sk now has an amplitude which is 1 minus 4/n into 1/square root of n, which is what is in psi, plus 2/square root of n. So effectively, state sk underwent amplitude magnification. And this is where, if you had an oracle that told you, hey, go in this direction, then you go in that direction and apply this amplitude magnification, and that helps you converge to the solution that you're looking for. So when you're trying to do search, you're trying to do oracle and reflection transforms. Grover's algorithm, for example, uses these kinds of techniques for search. Then want to finally give you an example of annealing-based systems, D-wave systems, which is a mesh-based quantum computer. It's a lattice of tiny superconducting devices and chilled pretty close to absolute zero. And what you're trying to do is searching for the lowest energy point, trying to minimize an objective function. So you're trying to, and this can be used for optimization problems, any optimization problem, whether it's for supply chain or energy optimization in the network, or any problem that you can craft where you need to optimize and find the minimum of the objective function can be modeled here. And the quantum computer considers all possibilities simultaneously and tries to find values of states that help it achieve the lowest energy. This kind of computer looks like this, and um, a lot of qubits all interconnected with each other, kind of thing. Now, they have some degree of connectivity. So in terms of how the how many edges are there on, if every node is every qubit is a node in a graph, the degree of the node is how many connections it has to other qubits. And now it's possible that you might be trying to solve a graph problem which has maybe more connectivity that is needed than what is physically available. In that case, you actually transform it by splitting it up into two qubits, for example, and so that the combination of the two qubits has enough degree to kind of reach out to other qubits. So you may have a physical to virtual mapping in these problems. So to actually match up the actual connectivity required in the graph that for the problem that you're trying to solve. And these systems have quantum processing units and the instructions that you give them to execute. They're called quantum machine instructions. And the typical problem that you would solve is like a quadratic unconstrained binary optimization. It's called a QUBO. So each of these variables, you're trying to find a value for it to solve your optimization problem. And so there are different terms here. If you just have xi, then that's the state of one of the qubits. Then the qii term in front of it is called a self-coupling coefficient. But then if you have xi, xj, then that is two qubits interacting with each other. And qij is called the cross-coupling coefficient, which is the strength of the connection between the two qubits that is programmed. So if you say this is the strength of if this is qij for the problem, then for between these two qubits, the system will program that connection to that strength. And then you let it run and settle to let the system run and settle down to a low energy state, which becomes a solution to the problem. So and the interesting part about this is that let's say you have variable, this variable can be 0 or 1, then x squared will take on value 0 or 1. So you can replace x squared with x in the energy function. X cube is also, x cube will also go to 0, take on values between 0 and 1. So effectively, any higher order functions can actually get reduced to this kind of quadratic kind of function because these values that they're taking are 0 or 1, for example. And if the values that, let's say it's going from 0 to 32 or something, you just scale it down and then it just takes values between 0 and 1. So then that essentially means that the coefficients have to be scaled appropriately so that the variables take on values between 0 and 1. That helps you solve any higher order optimization problem as well. And the different variations on these on the optimization models. And here, to give an example, for example, here there are you have 4 qubits, and these are the interconnections between these qubits. So the number of interconnections is n choose 2. So 4 into 3 by 2. So 6. So 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and then 2, 3. So what you're trying to do is trying to find the minimum energy solution, for example. And here's a simple example, so you can see what's going on. And then you'll find that the solution is 0011, which means it tries to keep 2 and 3 on and 0 and 1 off. And why is that? Well, 3 has a self-coupling coefficient which is negative. So that reduces the energy. But you can see qubit 2 has a self-coupling of 2.1. So really it shouldn't be on. But then if you look, if you know you're going to keep 3 on, if you look at the coefficient between 2 and 3, that's minus 3.22. That's more negative than the self-coupling coefficient of 2.1, which forces 2 to turn on, because if 2 is on, then actually the overall contribution is negative. And so that lowers the energy. But then if you look at 0 and 1, for example, their self-coupling coefficients are high. Cross-coupling coefficients also high, they leading to higher energy states. So the system pushes 0 and 1 state bits to 0, and then 2 and 3 to 1. So the solution becomes 0011 in the system. And then you can evaluate the energy for the system, for example, which will be minus 2.4 plus 2.1 minus 3.22. And that becomes the total solution, total energy in the solution. And the 0 and 1 don't matter. So similarly, this is like a 5 qubit thing. You can do a similar calculation here. And you can work with these computers directly with D-Wave, or Amazon has AWS Bracket as a library that allows you to access any quantum computer. But you can see when you're trying to solve any problem, what you have to do in this kind of an optimization problem is figure out what the coefficients are. And then once you've set it up, once you've set up the queue, for example, then you're submitting that queue value in that queue matrix into the optimizer, and that's all you have to do. And in the background, the quantum computer is running, trying to find the minimum energy solution. All you had to do was define the variables in your problem, define the cross-coupling and self-coupling coefficient values, and that's it. And then you submit it through the cloud and it gives you an answer. So, for example, here, there's a graph partitioning problem that got solved. So it's actually pretty easy to use these computers, because all you have to do is set up this matrix and then submit it. And so that's about it. I just wanted to give you guys an introduction. So overall, we've seen gate-based computation and annealing-based computation. These are some references, and happy to take any questions at this time. So you can solve factorization related problems, search related problems, optimization related problems, and so on. These days, though, there is a problem with all of these quantum computers, in that the qubits are not reliable. So if, for example, if you go through the IBM's QIS kit simulator, you'll get an answer which is accurate. But then if you submit it to the quantum computer, and we can submit it and it'll get queued, and then it'll come back with an answer. That answer may be different and wrong, actually, sometimes. But that's because the qubits are not reliable at this time. So now the National Science Foundation has set an objective to actually asking scientists to go back to the physics of these machines to make sure that the computation is more reliable. Right now, there is too much entropy in the system, and the answers are not reliable. So it may take a few more years for these things to be truly realized. And even IBM, although it announced its 1,000-qubit quantum computer, it said from now on, we're not going to focus on adding more qubits to our systems, but we are going to focus on trying to make these systems more reliable. So that's still there. That problem is there. Before Gen AI happened, quantum compute and before, as crypto was going down, quantum was kind of taking prominence. So a lot of effort went into trying to see if we could use quantum computers, but then people realized that, hey, um, these systems are not yet ready. So, but we could continue to still develop these kinds of algorithms, even in a quantum-inspired manner, and classically even simulate them, and hopefully be ready as well when the quantum computers get more reliable. Right now, there's a lot of effort in actually in trying to control these errors. So just like in a communication system, you send some bits, but you also have send redundant bits for error correction. In quantum computation, we also have a similar situation. So we try to use so the effective number of qubits is reduced because you're trying to do some sort of redundant computation there to correct possible errors in the system. So that's one way of trying to fix this. But at the same time, the qubits that are not reliable are unpredictable. I mean, a qubit that's reliable now may become unreliable later. So which qubits are reliable or not is also a function of time. And so people are actually trying to identify which qubits are good, and also trying to build compilers that will send the computation to the qubits that are more reliable and so on. So a lot of effort to work around these issues related to reliability of qubits at this time. And additional and more significantly, a lot of effort and a lot of funding from the NSF into universities, for example, to build uh, more reliable quantum computers from the physics side of things itself, while computer scientists continue to develop the algorithms. So that's the current state at this time.
So another question was, let's see if there's a lot of. Let's. What do you want? Just muted. Muted.
Sorry, I can't hear. What's the question?
Difficult if someone's in the same room as the presentation, because then it starts that echoing. He might need to type it into the chat instead.
Dilip, while we're waiting for the other question, this is probably could be a silly question. Comparing the quantum computers to traditional computing, is there a generalized or standardized operating system between IBM and the other vendors? I'm just curious, is there one platform to run this all, or does each manufacturer have their own individual operating system?
Yeah, so right now, each manufacturer provides an interface to access their computer, but AWS tries to create a uniform interface through AWS Bracket. Bracket is from the quantum inspired thing of BRAKET. So you could go through AWS, or you could directly interact with each quantum computer individually. Like you could just go directly talk to IBM's quantum computer or D-Wave's quantum computer through the cloud, or you could go through AWS as well. But it is, and they try to create some sort of an abstraction so that it tries to be somewhat seamless. But yeah, internally though, each of these quantum computers have their own libraries. They also come with simulators and stuff like that. IBM has this QIS kit simulator that people can use for experimenting with these computations.
Thank you.
Sure.
Can you hear me now, Dilip?
Pardon?
Can you hear me? Now
Yeah,
it's
yeah.
better.
Yeah,
So
yeah.
you mentioned that some qubits are reliable and others are not. So is it some portion on the hardware that you see that is not reliable, or does that thing move around also? So I didn't understand what you mean by some are reliable and some aren't.
Oh, it's just because of there's some temperature effects in the system, and that causes some uncertainty in the processing, in the in the physical processing. If you try to do a simulation, or with a simulator with perfect execution, then it'll come up with an answer. But the physical qubits actually, because of the entropy that's there, they may come up with a slightly different answer, because uh, although you might expect that qubit should have taken on a particular state or particular amplitude, it actually goes to a different state. And that's just because of the temperature in the system. Think of Gen AI, for example. There's entropy in our LLMs, right? There is some probability with which the LLM produces an output, and it produces outputs that are higher, that have higher probability more often, and but still produces the other possible outputs as well that are have low probability. So even here, that's the case, in the sense, for the most part, they're trying to execute reliably, but they could flip over to the other side just because of the temperature in the system. And unfortunately, as a function of time, these qubits, which qubits become reliable and unreliable, keeps changing. So what you try to do is try to keep redundancy in the system, in the processing, so that you essentially build an error correction into the computation, just like we build errors into communication systems, so that on the other side, with the redundancy, you recover the signal that you got. So
And
the only problem is, we are trying to get more qubits to solve more complex problems, but now effectively the effective number of qubits is reduced, because we have to use some of them for redundancy, so for error correction and so on.
The other thing I didn't understand, you said that certain things, the amplitude starts to rise up, and that is most likely the solution.
Yeah.
But is that where you have other class of problems where you're looking at a range of solutions? So does it like it's only one amplitude, or you can see multiple?
No. Good. So you can have multiple solutions to the problem, and so an energy function can have multiple minima. So the ones that are possible solutions will go up in amplitude, and well, the others will go down in amplitude as the system evolves and to its lower energy states and so on. So, and then if you take a measurement, one of these possible higher probable states will emerge as a solution. So what they try to do is try to repeat the solution multiple times, with maybe different initial states and things like that, and see where they converge. But the interesting thing about a quantum computer is it actually is exploring all possible multiple solutions all at the same time, because of the superposition of states. If you try to do a Monte Carlo simulation on a classical computer, you will start with some initial state and then it'll just converge to something. But here, what you're trying to do is actually evaluate many different things from that initial state. So you're going left, you're going right, you're going up, down, northeast, southwest, that kind of thing, exploring all directions concurrently. And then some of them may emerge as low energy states. And so when you take a measurement, you'll pick out one of them and say, that's my answer. And then when you repeat these searches many times, then hopefully you'll find the lowest energy solution a few times, and then you say, okay, yeah, that's the best answer in the system. So.
The other thing I wanted to get a flavor for the number that you showed IBM ranges from like the lower 2 digits to I think almost like some 1,000 qubits you showed, right? While the
Yeah.
other ones are smaller. So, what is the motivation behind trying the large? Is to find out how they behave in more things, or is that very expensive, or just wanted to get a feel as to where we are, right?
Yeah, with regard to, for example, encryption and things like that, if you need, say, if you need to break like 512 bit key, you need with elliptic curves or something, you need 1/3 the number of qubits. So so the greater the number of qubits that you have, the higher the dimension in cryptography that you can try to crack as a problem. So that's where they try to go and to support more and more qubits to solve more higher dimensional problems, more complex problems with regard to factorization and so on. And uh, but a lot of the focus now is going towards making the systems more reliable. But yeah, recently IBM announced a 1,000+ qubit gate-based quantum computer, which is a big milestone. But what they've said is we're not going to try to add any more qubits into this. We have to go back to the physics. So.
Dilip, this is Sri again. One question. Unlike traditional computers that are so portable, they're small, that could be taken anywhere you can think of. Quantum computers, I'm guessing, are they like the traditional mainframes that usually take like multiple rooms at a time? I don't know how big these are scale-wise, and do you see them being portable in the future at all?
So Intel has come up with a 12-qubit chip, so they're trying. And you have to imagine that Intel would be the one who would try to do something like this. But most quantum computers are in a super cool state, occupying a large amount of space and remotely accessed through the cloud. So be very hard to it'll be a while before we find it on a smartphone or something like that, I think. And that's where we have to see what's the computational complexity of the problem that we are trying to solve. And it has to be worth the latency of going to that computer, setting up the problem, going through the cloud and going to the computer, the latencies involved in setting up the machine, and then the result coming back. So, and if all that round trip latency and execution time is higher than doing it classically for a lower dimensional problem, then maybe you don't need the quantum computer. So that's where, they're trying to make these quantum computers more complex and to solve more difficult problems, in the sense, have more computational capability. And yet we want them to be closer to us so we can minimize latencies to access them. Yeah. But someday, yeah, maybe it'll happen. People are looking at trying to make this work, even say at room temperature and things like that. Trying to work with the entropy in the system, knowing that there is entropy with the higher temperature, and still try to do some probabilistic computation. But there hasn't been much success there, and so most of these computers need the supercooling, and that takes up a lot of space and a lot of energy as well to kind of maintain them. So
hi Dilip, this is Ganges. Thank you for the presentation. So comparing with the different types of quantum computers you described, and how it is compared with the IonQ, because they have commercial grade quantum computers, and they are very much talkative in the industry right now with the quantum computing for the commercial use cases as well, which is like sort of away from the research community to the commercial usage. What's your take on that?
Yeah, they're all trying. There's also QCI. So a lot of companies coming up, a lot of physicists trying to convert their research projects into commercial quantum computers. But across the board, the reliability is an issue across all of them at this point. So although that the hype quantum computing went through this hype cycle, it has come down because of this issue at this time. So, but they are trying, all of them try to, even D-Wave, QCI, they all try to market their solutions. The hope is that, as you submit it to this quantum computer, the result will come out faster compared to a classical computer, or the quality of the solution will come out better because it's searching through a superposition of states. And in the same time as a classical computer, the quantum computer should give you a better result because it searches the space better. So, or a combination of both, it gives you a better quality solution in lesser time. But they're trying, and they've built these machines, they've built APIs, but yeah, well, there was the chemistry professor who was trying to do some molecular computations and stuff like that, and he felt that submitting to the D-Wave quantum computer did give him a better quality result, although he didn't save much on time because of the latencies involved and all of that. So there is some hope there. We don't know if it was just truly because of the quantum execution, or whether, the search ended up coming up with a better answer on the other computer. So, and whether whether you can consistently predict that you will get a better quality answer with the quantum computer, not sure. So at this point, because of the issues with the quantum computation at this point, because of the reliability aspects.
Thank you.
But yeah,
So
they're all trying. IonQ is all of these companies are taking their time actually now to kind of go back to the drawing board to figure out how to fix these kinds of issues that are there, from the reliability angle. Yeah.
Thank you.
Sure. Yeah.
All right, folks. Hey, Dilip, thanks a lot for this very insightful talk. This was real fun, and thanks for giving us time for it. Sure,
Asif. Yeah. We can get into a more complex talk, a more advanced talk. It's at some other point.
Yeah.
Sachin here is saying we'll need a few years
To understand.
It's a deep topic. That's right.
Yeah. Cool. Thanks, Asif. Happy to contribute.
Thank you. And thanks everyone for the participation and for being part of the Support Vectors learning community. I look forward to seeing you again. Next week, there will not be a meetup. I will be out of town, and Support Vectors will actually be closed next Wednesday. We'll take it up again the subsequent week. So there'll be a 1 week gap in the meetups. As some of you know, I'll be flying over to Carnegie Mellon University because I have to situate my daughter there. She's going for graduate school in machine learning. So I'll see you guys 2 weeks from now. And Dilip, once again, thanks a lot. And I hope to see you in California soon. You're having a beautiful spring season.
Yeah, looking forward, Asif. Yeah. Hey, and good luck to Shafali. Yeah.
That's the reason I'm going off for dinner with her. Bye. Bye.